Hi, I'm Marc Masana, and I will be presenting the paper Ternary Feature Masks, Zero Forgetting for Task-Incremental Learning. When we learn a task and afterwards we want to learn a new task without access to the previous one, usually the previous knowledge has a lower performance. And as if we do that in an incremental setting, that tends to be the case that the knowledge from the beginning is forgotten, and this is known as catastrophic forgetting. Some state-of-the-art methods focus on having zero forgetting and trying to keep the knowledge from previous tasks completely unchanged as new tasks are learned, but this comes as the cost of some overhead, and those methods that allow for some forgetting of previous knowledge can have a much lower overhead impact, but they do at the cost of having some kind of forgetting. And the problem with forgetting is that we usually don't know a priori how much it will affect. So the baseline that we could think of for keeping all of the knowledge that we have is that we would dedicate activations on the weights related to them, completely separate one of the other, creating different subnetworks inside the network. And these will guarantee that we have zero forgetting when learning new tasks. However, this also means that there will be no knowledge that will be used from previous tasks when learning a new one. What we present is that after learning the first task on a set of activations on their corresponding weights, then we can choose to extend those activations and the corresponding weights for learning a new task. However, when learning this new task, we will only be able to modify the weights that belong to these two connections between the new activations that we've added and those activations on the previous weights. However, previous knowledge here, signaled in black, will not be modified. In order to do that, what we do is that we allow the information to be seen in the forward pass for the black connections, but they will not be able to be modified on the backward pass. And this guarantees that whenever we want to revisit one of the tasks, we will be able to have it without no forgetting at all. And we can extend that over and over, and the idea is that whenever you have more tasks, then you also have more information that you could reuse from previous tasks. On top of that, this information is fixed, and therefore what we propose is that if we allow a shift and a scale applied to each of those activations when learning a new task, it allows for having a bit more wiggle room for learning to use the fixed features already learned in a much valuable way. In our experimental setting, when we look at the overhead growth, which was the first of the axes that we discussed, our methods in blue are clearly equal or better than the best methods in the state of the art in this logarithmic scale, where we see that it basically has very to no significant overhead over the network. However, whenever we move to the experimental setting, we see that in comparison to this same method, we do much better, and we compare similar or better than the method that performs the best at this time on the state of the art. So it is also noticeable that we test these in Tiny ImageNet for 3 different splits. One of them is random, and the other one has a semantic meaning or a large first task. And when doing it with a large first task, our method does significantly better. We assume, especially because of what we were explaining before, that the information from the first task can be reused for the other tasks. It provides an advantage over learning the tasks in smaller chunks. We also do experiments on ImageNet, where we also obtain better results than the rest of the state of the art. And in general, the idea is that we propose a method that doesn't suffer from any forgetting at all, that allows to use the masks on the activations instead of the weights in order to reduce significantly by more than 2 orders of magnitude the overhead applied to the network. And we propose to use task-specific feature normalization so that we can adjust the knowledge that we've learned from previous tasks to the new tasks. And we also want to point out that for some of these data sets, it is interesting to look at the semantic proposed split for tiny ImageNet in this case, or starting from a larger task, because they seem to be a bit more challenging settings. Code will be provided at GitHub. Thank you for your attention.